Welcome back. So you and I have had a good chat about chemical reactions and the chemical equations we use to describe them. Now that we've got that under our belt, we can start talking about a variety of different types of chemical reactions. For the next couple of topics, it will be useful for you to keep your table of common cations and anions handy. I won't specifically be referring to it all the time, but we will make and break some ionic compounds, and so if you're trying to help get your head around how they're making and breaking, knowing those charges on those cations and anions may be useful from time to time. So we're going to start by talking a bit more about solutions, something we've introduced already, but we'll quickly rehash that. Here I've got a photo of a few different chemical solutions in the lab. Chemists can actually tell quite a lot about a solution just at a glance. So some of the colours that you can see here are quite typical of particular chemical species. We're not going to study that so much as look at why something does dissolve in water or why something doesn't, why something makes a solution. So once again, what is a solution? A solution is made by taking a solute and dissolving it in a solvent. If I take a sugar solution as an example, here I've got a sugar cube, that would be my solute. I'm going to put that into a glass of water, that's my solvent, and all of that mixed together, that becomes my solution. So lots of solutions around you, and again we've discussed a few examples already, things like your drinking water or the ocean, seawater. Soft drinks are a good example, maybe a glass of wine. These are all different examples of solutions, one material dissolved in another. For the solutions we're talking about, we're going to focus on those aqueous solutions, solutions that are made up in water. That's our primary interest in this topic. So if we're going to understand the way materials behave and why they do or don't dissolve in water, we really need to better understand the behaviour of water. So we're going to take a bit of a trip down memory lane. We've discussed this concept a little bit already, but I really want to hammer it home. I've got a water molecule here for you on screen. Oxygen at one end, hydrogens at the other. Do you remember electronegativity? The measure of how much atoms want to take on that share of electrons when they're forming a covalent bond? Well, if I pop up on screen the electronegativities here for water, you can see that oxygen is notably higher than hydrogen. This is a polar covalent molecule. The oxygen wants those electrons a bit more than the hydrogen, so the electrons get pulled to one end of the molecule. And this creates a polar molecule where one end is slightly negative and one end is slightly positive. You recall all that? That's going to play a big role in the way that water interacts with other materials and help decide which materials it will form solutions with and which ones it won't. So let's have a look at an example now. I'm going to introduce another molecule. I'm going to introduce ammonia to our system here. So ammonia, NH3, all the hydrogens on one side, the nitrogen on the other. Ammonia is also a polar molecule. The nitrogen, more electronegative than the hydrogens, pulls the electrons towards its end of the bond. So once again, we end up with a polar molecule. If we're then trying to picture what would happen if I mixed ammonia with water, would it mix in and dissolve, or will it want to stay completely separate or apart? Understanding this polarity, the polar molecules, is the key. If you look at these two, I've got one with a slightly negative end and the other with a slightly positive end nearby. We've talked about this idea before. You played with magnets as kids, positive, negative, they'll be attracted to one another. And that's exactly what happens. Negative end of one molecule gets attracted to the positive end in another. And in doing so, they're able to mix, they're able to stay together. So by knowing that ammonia is a polar molecule like water, we can predict that it will dissolve in water. In fact, we can even write an equation to show this. So ammonia is normally a gas, but if you put it in water, which is why I've got the little water above the arrow there, it will become aqueous. It will dissolve in water. And this runs a common theme people use to help them describe this is like dissolves like. So polar molecules, like water, will dissolve or mix with other polar molecules, like ammonia. They'll also explain some of your household observations. We often hear the term oil and water don't mix. This is exactly why. Oil is just made a long chain, usually made of carbon and hydrogen atoms, sometimes one or two oxygens, but mostly hydrogen and carbon. Those atoms both have very similar electronegativities. It's a non-polar molecule, which means it has no means of being attracted to the water. Because it's not at all attracted, they won't mix. So if you pour water into the pot, if you're cooking pasta or something on the stove, the oil will immediately come to the top. Doesn't want anything to do with the water, so they won't mix. Okay, so that'll do for this topic. We'll take a break. We've discussed how covalent compounds dissolve in water. that polar molecules will dissolve in water because it's a polar molecule, and that non-polar compounds, non-polar molecules won't. In the next topic, we'll have a look at ionic compounds, and then we'll have a look at some examples of both ionic and molecular or covalent compounds dissolving in water.